أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. Assalamu alaikum warahmatullah. Welcome to the third lecture of this week 3. We were studying chapter number 11 of our course book, that is metal casting processes. In this lecture we have gone through the sand casting and the various features of the sand casting. Then we discussed the different types of expandable mold casting in the last two lectures. Then we discussed the permanent mold casting. In the permanent mold casting, we were discussing that it has three subtypes. The first one is called the basic permanent mold casting, which is also known as the gravity die casting, because in this kind of the casting metal flows by the effect of gravity. Then the second type of the permanent mold casting was the die casting, which is also known as the pressure die casting, because in this kind of the casting the metal molten material is forced into the die cavity or the mold by the effect of external pressure. Then the last one and the third type of the permanent mold casting is the centrifugal casting. What is the centrifugal casting? As the name suggests, in this kind of the casting we utilize a centrifugal force to distribute the molten material into the mold cavity. So it's a family of casting processes in which the mold is rotated at a high speed. So the centrifugal force distributes molten material to outer region of the die cavity. As we have studied that the centrifugal force is acted outwards, right? So when the molten material is rotated at a very high speed in the mold, so the centrifugal force forces the molten material towards the outer region of the mold cavity. So the three common types of the centrifugal casting are the true centrifugal casting, then we have the semi-centrifugal casting, and the centrifuge casting. If you go to the true centrifugal casting, in this kind of the casting, molten metal is poured into rotating mold to produce a tubular part. So this is the common schematic of the true centrifugal casting. We have a mold cavity, this one, and we have the two drive rolls which are utilized to rotate the mold at a very high speed. And this is a section view. So we have a hollow mold, and this is the pouring basin from where we pour the molten material into the mold cavity, and these are the driver rolls which are rotating the mold at a very high speed. So in some operations mold is rotated before pouring the molten material, so that mold is already rotating at a high speed, and during that rotation we are pouring the molten material into the mold cavity, while in some cases we first pour the molten material and then the rotation of the mold starts. So this kind of the casting is mostly used to design pipes, tubes, bushing, rings and other hollow parts. So outside shape of this casting, we can have the round shape, we can have the octagonal shape, we can have the hexagonal shape, but the inside shape will be perfectly round because of the symmetric forces acting along, because we have the radial forces that are acting on the inside of the material. Outside shape can be anything. Let's suppose if we have a mold shape like this one, let's suppose, probably so the centrifugal force will distribute the molten material like this. So our outer shape would be like hexagonal, but inside would be a perfect round because of the radial symmetric forces that are acting on the inside of the molten material. So in the case of the centrifugal casting, we have two kind of orientation. Centrifugal casting, true centrifugal casting can be performed horizontally or it can be performed vertically. So we'll just take the case of the horizontal casting. So let us consider a mold that is rotating at a high speed. So the centrifugal force that is acting on this molten material would be equals to, as you know, centrifugal force equals to mv square by r, uh, where F is the force in Newton and m is the mass of the molten material in the kilograms. then V is the velocity here, and R is the inside diameter of the mold cavity. R is the inside diameter. So there is a factor called the G factor. There is a factor called the G factor that is used to determine that how fast a mold should be rotated, so that we can perform the centrifugal casting without rain of the molten material. So what is the G factor? G factor is equals to it's equals to centrifugal force divided by the weight of the molten material. So we have centrifugal force equals to mv square by r into weight. So we cancel out this one. We have remaining is a v square by rg. So this is the G factor. But as you know, we have the velocity in terms of meter per second, but it's in a rotational motion, so we will convert this into the revolutions per minute. So we can simply convert this velocity v into rotational, that is equals to 2 pi r n. Let me write it correctly. And to convert it to the minutes, we have 60, so we can have pi rn by 30. Now we can simply put this value into the formula of G factor. So the GF would be equals to that is pi rn by 30 whole square divided by rg, and we have r square. You can cancel out this r with that one, so we have gf equals to pi n by 30 square by g. Now we can find out we can solve it for the n, because we need to identify the revolutions per minute for this mode. So we can have it as a G into G factor into 30 square we have r here also divided by r into pi square. If we solve it for the n, we will have n equals to 30, we have the pi under root, we have gf into g divided by, you can write it in the terms of radius or you can write it in terms of diameter, so you have to add multiply 2 here. So this is how we can calculate the number of revolutions per minute for the mold cavity, and you should remember that here d is the internal diameter. Now few things, if the G factor is too low, if you have a very low G factor, so what will happen, it will not generate enough centrifugal force. So once the molten metal rotate and reaches at the top, it will start to rain down. If our G factor is low, it will generate lower centrifugal force. So when it reaches at the top, during rotation it will start to rain down, right? Or there will be slipping occur between the molten material and the mold wall, right? There will be a slipping between the molten material and the mold wall. So molten material is continuously changing its position as well. So it means that the speed of the mold is less than what it should be. So on the empirical basis, the GF value, G factor value should be around 60 to 80 for the horizontal centrifugal casting. Although also depends upon the material being casted, but this is the experimental observation that it should lie between 60 to 80 for the horizontal true centrifugal casting. It's not for everyone, only for the horizontal true centrifugal. Okay, one thing we need to make sure that that's the inside diameter of the mold cavity, or you should remember this one, it's the inside diameter of the mold cavity. So let's start solving this numerical problem. It says the true centrifugal casting operation is to perform horizontally to make a copper tube section, and the outside diameter, it's a diameter of the copper tube. So outside diameter of copper tube is 25 centimeter, and inside diameter of copper tube is 22.5 centimeter. It says what is the rotation speed required if a G factor of 65 is to be used. Now if you remember, the formula that we derive for the rotation speed was n equals to 30 by pi into 2g gf divided by the inside diameter of the mold cavity, right? So now start putting the value. We have 30 by pi under root 2 into 9.8. It says the GF should be 65. GF should be 65, and it says as this is the inside diameter of the mold, so you can see the inside diameter of the mold will be the outside diameter of the cast product, right? The inside diameter of the mold is the outside diameter of this blue cast product. So the outside diameter of copper tube is 25 centimeter. So this 25 centimeter is the inside diameter of our mold cavity. So we have 0.25 meter. Now we can solve it for this one. So solving this one, the number of revolutions required would be 684.03 revolutions per minute. So this mold should be rotated at this speed to perform this casting. Now the second case for this one is the vertical alignment. We can also perform true centrifugal casting in the vertical alignment, right? It's called a vertical true centrifugal casting. Let us divide this one. So we will have the mold cavity like this. If I draw the section view, let's suppose this is a mold cavity and we have poured the molten material and it is rotating at a high speed. It is rotating at a very high speed at certain revolutions per minute. So once the molten material settles down along the mold wall here, it's not visible. Once the molten material settles down along the mold walls, but there's one additional factor in the case of the vertical centrifugal casting, that is the gravity. So owing to this gravity, the thickness of this section is not the same at the top, is not the same as at the bottom, because of the effect of gravity the material tends to flow downward. So the tube or whatever we are casting is somewhat thicker at the bottom compared to the top. Whatever we are casting has a section or a thickness greater at the bottom compared to the top. So to take this into account, this change in thickness along the section of this cast product, we have a slight change in the formula for this revolution per minute, that is equals to n equals to 30 divided by pi under root 2 g length of the mold section and divide by RT square minus RB square, where L is the vertical length of the casting, this one is the L, and RT is the inside diameter, inside the radius at the top of the casting, and the RB is the inside radius at the bottom. Okay, so we can see here to have uh, a uniform thickness along the whole section. Let's suppose if you have a uniform thickness, there is no change in thickness, so it means RT should be equal to RB. If the thickness is same at the top as the bottom, if the thickness at the top is same as the bottom, so it means RT would be equal to RB, and it would be equals to 0. This denominator would be equal to 0, and it means our number of revolution would be equals to infinite. For uniform thickness, n would be equals to infinite, which is obviously practically not possible. So it means in the vertical centrifugal casting, true centrifugal casting, it's not possible to have a uniform thickness at the top and the bottom. There will be some change in thickness because of the effect of gravity. So that's why when we are casting any part using the vertical to centrifugal casting, we tends to make sure that the part length shouldn't be greater, the L should be as small as possible, but we can have the large diameters, right? But we tend to make a smaller length with the large diameter, like the bushings or rings, so they are preferred for this true centrifugal casting. So there are certain advantages for the centrifugal casting, true centrifugal casting itself. That is, it has the high density. The centrifugal casting itself has the high density. Okay, we'll see those advantages towards the end once we discuss some other types of the centrifugal casting. The second type of the centrifugal casting is the semi-centrifugal casting. So in this method, centrifugal force is used to produce solid casting. Like in the true centrifugal casting, it was used to produce the hollow sections like tube and pipes and other tubular parts. Rather, in this kind of the casting, it is used to make the solid products. So the rotation speed in the semi-centrifugal casting is usually set to the G factors around 15, while in the case of the true centrifugal casting, you remember the G factor was around, in the true centrifugal it was around 60 to 80, while in the case of the semi-centrifugal casting, this G factor is around 15. The molds are designed with a riser at the center to supply to feed the metal. So we have the riser at the center here. All this is the original part which we are casting, but we do have the riser here, so that if there's any shrinkage, it will compensate the shrinkage. And the density in the final, there's some change here because it's a solid section instead of the hollow, so there is a change in the density. The density is highest towards the edges while it reduces towards the center because of the effect of centrifugal force, right? The process is often used on a part in which the center of the casting is machined away. So we tend to use on such parts where we can have some machining in the center. Uh, Common examples that are casted using the semi-centrifugal casting are the wheels, pulleys. There are some common examples. Then the third type of the centrifugal casting, and you must have observed that this schematic for the semi-centrifugal casting is somewhat similar like a sand casting. It has a flask, it has a cope and drag, it has sand in it, it has a riser. So it is somewhat similar to the sand casting. In the only thing that is the main thing that is differentiating between them is that the mold is rotating at a high speed, so generating the centrifugal force. Now the last type of the centrifugal casting is the centrifuge casting. So in this kind of casting, the mold is designed with the part cavities located away from the axis. So we design if we desire some special geometries or cavities towards the edges, we use the centrifuge casting. So once we pour the molten material into the mold, it is distributed to these cavities by centrifugal force. So the centrifugal force help the molten material to reach these cavities, and it is mostly preferred for the smaller parts, and the radial symmetry of part is not required in the as in the other centrifugal casting. So it is not a greater requirement that should be radially symmetric on both sides of the axis. So again, it has some rotating table. We have the drag and the cope, the casting with some geometries towards the edges, and there's a runner and the riser here, and kind of the pouring cup. So that was the end of the centrifugal casting, and so to the end of the permanent mold casting and the casting processes, all kind of casting processes. Although we have left some less important types of the casting process, so I would recommend you to go to the book and study section number 11.3.4 of your course book. And it includes the following types. It has the squeeze casting, it has the liquid metal forging, which is a kind of a casting also. You should be aware with these terminologies. And it's a section of only half page. Semi-solid metal casting, and We have rheology, rheocasting, and molding and casting. So you should be aware with all these terminologies. Go to this section of your textbook and read all these types. Okay, so this is the practically end of the types of the casting we will discuss in this our subject. So now we will move towards the last section of this chapter, that is the foundry practices. So the foundry practices, in this section of the foundry practices, we are going to discuss three uh, aspects of the foundry. The first one is the furnace, the types of the furnaces that are being used in the foundries, and the post casting operations such as cleaning, heat treatment operations, and the casting quality, how to overcome the defects that are produced in various casting processes. So we will start with the furnaces. So the common furnaces that are used in the foundries are cupolas, the direct fuel fired furnace, crucible furnace, electric arc furnace, and the induction furnace. The furnace which is mostly used, especially for the cast iron, that is the cupolas furnace. So what is the cupolas furnace? Cupolas is a vertical cylindrical furnace equipped with a tapping spout. As you can see here, there is a tapping spout here. It's a large cylindrical shape that is equipped with the tapping spout near its base. So cupolas are used only for melting cast iron. They're primarily used for melting cast iron. You can write it down here. It is used for cast iron. Although there are other furnaces as well which can uh, melt the cast iron, but we prefer the cupolas furnace because it has the largest amount of tonnage for melting the cast iron. So the general construction of the cupolas furnace, that it has the outer exterior shell, which and on inside it has some refractory lining, and we have a floor from where we add the charge into the furnace. And what is charge? Uh, so this charge is basically, this one is charge, and what this charge is, this charge is a mixture of iron which we are melting plus coke plus flux, and we will see what the coke and the flux are in this furnace. Then with the charging, we have blower to supply the fresh air for supporting the combustion process. We have a tapping spout to take out the molten metal, and we have the slag spout from where we remove the slag. So what is the charge? Basically, charge is whatever we feed into the furnace for melting the material. So it has the iron, which is the primary material which we are melting here. It has a coke. Coke is a fuel used to heat the furnace. It's a pure form of carbon. It's like a pure carbon which is used to support the combustion process. This coke is the, you can say, it's pure carbon for combustion process. It supports the combustion process. Then we have the flux. Flux is, in this case, is mostly limestone. The flux used is a limestone here. It reacts with the ash once it is combusted. So there's a ash formation. So the flux reacts with this ashes and other impurities in here to form a waste material that's called the slag. We have the iron, which is a primary primary material which we are going to melt. We have the coke, that is a pure form of carbon. And why do we add the coke? To support the combustion process. So when this coke is combusted, it forms ash. So the flux reacts with that ash and other impurities, because ash is an impurity here. So it reacts with that ash and other impurities to form a slag. So the purpose of slag is the slag forms a protective layer over the molten material. So the molten material at the bottom is protected from the internal environment of the furnace, so that there is no reaction between the molten material and the internal other gases, so that we can have the pure form. So the once the molten material settles down toward the bottom, we can take it out using the tapping spout. Then the second type of the furnace that we used here in the foundries is a direct fuel fired furnace. So in the direct fuel fired furnace, it contains a small open hearth mat. It is like a we have a furnace wall, and it is an open hearth here, where we feed the metallic charge. Mm, and we have a fuel burners. Either you can use the natural gas as a fuel on the walls. So there is a burner at this wall. We can have the burner on the side wall as well, right? There are burners on the side wall which performs actual heating process. And the roof of the furnace is designed in such a way that it reflects the flame towards the material. So if there's a flame, so it will reflect down towards the material. So at the bottom of this furnace, we have a tap, so that once the material is poured is melted, we can take out the molten material. So this is a direct fuel fired furnace. As the name suggests, the fuel is in the direct contact with the material. The fuel is in the direct contact with the material. That's why it is a direct fuel fired furnace. So the common material that are melted using this furnace used in this furnace includes copper and the aluminum based alloy. Actually non-ferrous material. Copper based alloys, aluminum, or some other non-ferrous material. You can go through the book to read the details. The third type of the furnace that is used in the foundries is termed as the crucible furnace. These furnaces melt the metal without direct contact. In the previous one, we have the direct fuel fired furnace, because the fuel, the burning flame, was in the direct contact with the material. While this crucible furnace, it is also known as the you can say indirect. It's an indirect fuel fired, because there is no direct contact on the fuel between the fuel and the material, right? So the three types of crucible furnace are used in the foundries. The first one is termed as a lift out furnace. This first one is called as a lift out crucible furnace. Then the second one is called as a stationary crucible furnace. This one is a stationary crucible furnace. And the third one we have as a ladle furnace, or the tilting pot furnace. That tilting is the third one, the tilting pot furnace. So in the lift out crucible furnace, the crucible place in a furnace and heat it sufficiently to melt the charge. So we have a crucible here, and this crucible as a whole is placed within the furnace where it is heated until we have the molten material, and then this crucible is lifted out using the crane. That's what's called a lift out crucible furnace. We lift out the crucible. Then in the second one, we have the crucible that is fixed inside the furnace, and the material is charged into the crucible where it is heated and melted. Once you have the molten pool, we can take out the molten material as per our requirement using another crucible. And the third one, tilting pot furnace, where uh, we have the crucible which has a mechanism for tilting it by any mechanical means, and we use the fuel, either the flame via the natural gas, which is used to heat the material until we achieve the molten state. So once we have the molten pool, we can tilt this pot, and we can take out the molten material. Then there's another type of the furnace that is termed as the electric arc furnace. Electric arc furnace is mostly used for the high melting point material, and it also has a very high production rate. So in this type of the furnace, the charge is melted by heat generated by electric charges. So the various configuration available. We can have the 2 electrodes or 3 electrodes in the furnace. The power consumption is very high. In the electric arc furnace, you have a very high power consumption. It might range up to various 50,000 watts. So because of this very high consumption power, they have the high melting capacity as well. So the melting capacity ranges from melting capacity for the it ranges from 23,000 to 45,000 kilogram per hour. It can melt this amount of the metal in an hour, or you can say 25 to 50 tons per hour, and they are mostly used for casting steels. Right. Then there's another type, the last type of the furnace that are used in the foundries, that is known as the induction furnace. So as the name suggests, induction furnace uses the induction current for generating the heat. So it uses the alternating current passing through coils. So the passing through coil to develop a magnetic field, right, in the metal, and the resultant induced current causes the rapid heating. So once we have the magnetic field which induces the current into the material, and because of this induced current, there is a rapid heating and melting of the material. So it can generate a very high amount of temperature. It can melt almost any material, and it's somewhat very pure form of the molten material which you achieve, but it's also very costly, and the operation cost is also very high for the induction furnace. And one another advantage for the induction furnace is because of this magnetic field, there is a continuous stirring operation within the molten material. So there's a continuous stirring going on within the molten pool. So it doesn't allow formation of pores, or you can say the entrapment of the gases into the material. So this is the end of this section of furnaces in the foundry practices. In the next lecture, we are going to see some post casting processes like the cleaning, pouring, and the heat treatment. Then we are going to see some quality check methods that are used in the foundry to identify the various defects in our cast product. So that's all for this lecture.